Hello there. This lecture is called Linear Independence. And the definition of linear independence will be quite useful throughout the study of linear algebra. It will provide a sense of two things. Once we have at hand a definition of independence, this definition will be based on what we have defined as a linear combination, and it will allow us to classify sets as either independent, and if the set is not independent, then you're probably guessing what it will be called. It will be called dependent. So either we have linear independence or we have linear dependence. And so the dependence, when a set is linearly dependent, there will be a sense of being redundant. These definitions of independence will bring to light whether or not a set may have members, that can. There will be a sense of being redundant, and you will see what I mean. And so, interesting thing about the study of linear independence is that it will allow one to kind of select of come up with subsets that are much more efficient, subsets that will get rid of that those redundancies, and will stay on target for specifically we'll be looking at sets that are linearly independent and also have a spanning property. So they can the set can be both a spanning set and also linearly independent. We'll have a name for that, but let's get started. So let's see. So we consider this example in which we have four members, a set here called T, with four elements, four members, W1, W2, W3, and W4. And the span of this set we say is an infinite set, because remember, the span is the set of all possible linear combinations. So we say that the span is an infinite set because this is in the same spirit as when we express the solution set of a linear system of equations, and we have free variables and dependent variables. And so for each evaluation of the free variables at specific values, you're going to have one specific member of that solution set. And so it's similar for the span being a set that contains infinitely many members or infinitely many elements. Okay, so we are going to consider the following. So here is a vector that we call z sub 2. This vector is something not that difficult to verify, that is a solution of this specific homogeneous system. And we're going to do the following. So we're going to do this verification. So notice that by reading the coefficients here, we write the coefficients on the side. In this linear combination, we have 2, 3, 0, and 1. Okay, so this being a member of the solution set, this vector is what allows us to write this linear combination. And since this is a member of the solution set of a linear system with coefficient matrix D and is a homogeneous system, that's why we write here on the right side of this equation, this is a vector equation, we're writing the 0 vector over there. But there will be an exploit here, and that follows from the fact of having one of these coefficients being 0, right? So there's a coefficient here that is 0, and that will allow us to argue in the following sense. Because of this vector equation, this is a vector equation, okay, is a vector equation on both sides of the equal sign, then we can solve for one variable, in this case the one that has coefficient equal to 1. This is very consistent with the type of calculations we were doing for linear systems. However, this is operating with vector equations, but solving for this vector W4 with coefficient 1 in terms of the vectors that have other coefficients, vectors W1, W2, then we can solve and write W4, 1W4 equals to this expression, right? So that tells us that from the original set of 4 vectors, it's possible to express one of those four vectors in terms of a smaller subset of this original set. Okay, so these are, if you're thinking dependent variables, that is a good way of thinking here. This equation says that whenever we encounter vector W4, we can replace it with a specific linear combination of W1 and W2. So there is then a sense of redundancy. In other words, if we're considering the span of T, okay, this can be reduced to the span of a subset of T. So in other words, these vectors, by excluding W4, this as a set of these three, this is a subset of the original set T. In other words, we could simply throw out W4 because W4 can be expressed in terms of considering all possible linear combinations in terms of vectors W1, W2, and W3. So W4, if you will, is in excess, is some type of excess of information when we're interested on the span of T. So the span of this set of vectors has not changed, but we are describing the span of a set of 3 vectors rather than the span of a set. So we're describing the span of 3 vectors rather than the span of 4 vectors. Okay, but the spans themselves, given that each of those is an infinite set, considering all possible combinations with all possible evaluations of scalars, each span is the same. It hasn't changed. So now we note that this is another solution, right? This vector is another solution of the homogeneous system with matrix of coefficients D. So this again, if you're wondering where this matrix of coefficients come from, right? So the reference here is one in the textbook. If you're wondering, in the textbook, then the reference is something that's called the archetype. Is the coefficient matrix in archetype D. So not too difficult to verify that Z1 is a member of the solution set of this linear system, and then we make use of the information, right? There is a scalar here. There is a scalar that is equal to 0, and so that allows us to write -3 times W1 minus 1 times W2 and then 1 times W3. I mean, this would be 0 times W4, and that would be equal to 0. But since this coefficient is 0, then there is no need of doing that. So that tells us that this reduces to 3 of these variables, and in fact is easy to solve for W3. These, again, both of these are vector equations. They are not scalar equations, they are vector equations. But then we express W3 in terms of W1, W2, very similar to what we do with dependent variables, expressing dependent variables in terms of free variables. Okay, and so this leads again to reducing the original set even farther. W3 is also in excess, right, and is redundant, and so we can basically throw out W3 in terms of coming up with a subset such that the span of that subset is equal to the span of the original set. So in this case, we have that the span of the set given by W1 and W2, that is exactly equal to what we wanted to consider. So this illustration leads to the definition of linear independence. But again, remember that we were calling W to be the span of the original set. This original set had 4 elements, and we have found that W is indeed, so this is still equal to the span of the original set that had 4 elements, right? So we have found a minimal set that would do the same job. And so W1 and W2 as a set collecting these two, this is a subset of the original set that contains 4 elements for W4, so W1, W2, W4, and W3, right? So this is the original set we call T, and this is a subset. And what we do, what we have done here in this discussion is come up with ways of eliminating 2 of those members and only work with a smaller set, because for purposes of describing the span, the original set was redundant. There were elements that, could be easily neglected. The span could very efficiently be described by only a smaller subset of the original set. So let's consider now a linear combination that is special, because a linear combination such that on the right side, first, the linear combination in terms of a vector equation, okay? So it's a linear combination that is equal to a vector, okay? And the other thing that makes this vector equation special is that this right side of the equation is the vector of zeros. So if you're thinking homogeneous system of equations, then that's also another good way of thinking on these type of problems, right? So it's like a homogeneous system. These vectors u1, u2, and u3 all the way through un, they are like the columns of the coefficient matrix in a homogeneous system. But let's just think of this linear combination equal to 0, and then we're going to give this vector equation a name. We're going to say that this equation is what will be referred to as a relation of linear dependence on the set. This is a finite set of vectors u1 through un. So if the only way to satisfy this vector equation is by setting all the scalars to take the trivial value of 0, so if every scalar is evaluated as 0, then this equation is indeed satisfied, because you have 0 scalar times a vector gives you 0 vector, and you'll be adding 0 vector plus 0 vector plus 0 vector, and then indeed that will be equal to the 0 vector. So if that is formed by choosing values of scalars such that they're all equal to 0, we would refer to that as a trivial relation of linear dependence. So then we say, if we are considering a set of vectors, we dub that set as dependent, linearly dependent, if there is a relation of linear dependence that is not trivial. In other words, if it's possible to find a set of values for the scalars such that not all of them are equal to 0 at the same time, at least some of them are 0, maybe some of them are 0, but not all of them are 0. If that is the case, that would be a non-trivial relation of linear dependence, and in such case, we would say that this set of vectors is linearly dependent. So when the only way of obtaining this relation of linear dependence is by setting all the scalars equal to 0, then we classify the set as a linearly independent set. So one of the things that came across in the illustration was the fact that we could express some of the elements of the set in terms of some of the other elements, and in that sense there was I was mentioning a sense of redundancy, right? So whenever the set is dependent, when we can find non-trivial values for the scalars and the set is dependent, it's possible to express some of those elements of the set in terms of the other ones.